In the previous lecture, we examined the following kinematics definitions: angular position, angular velocity, and angular acceleration. Now, if you go all the way back to chapter 2 with one-dimensional kinematics, ultimately what I did at the beginning of that chapter is I defined position, velocity, and acceleration. Then, of course, you understand what those quantities mean by using them. So we'll do the same thing here now for these rotational kinematics quantities, that is angular position, angular velocity, and angular acceleration. We'll begin by looking at a specific case, and that's going to be a situation involving constant angular acceleration. Okay, so rotational kinematics for constant angular acceleration alpha. What we're going to do is derive two expressions. We're going to derive angular velocity as a function of time, and then secondly, angular position as a function of time. As I begin this process, hopefully it's going to look very familiar to you because it's the exact same process that I went through in chapter 2 for translational one-dimensional kinematics. Okay, the first of our kinematics equations is going to be derived from the following. So here's the definition of angular acceleration. It's the derivative of angular velocity with respect to time. So then therefore, just like we did for translational acceleration back in chapter 2, we integrate to find velocity. Here we do the same thing. We start with angular acceleration and then integrate to find angular velocity. So let's go ahead and move the time dt to the other side of the expression, like so. Right here on the left-hand side, we're integrating over time from 0 to t. And then on the right-hand side, we're integrating over angular velocity from an initial value omega naught to a final value omega. Because alpha is constant here on the left-hand side, when you integrate this quantity here, you just end up with alpha times t. And then over here on the right-hand side of the expression, the variable that we're integrating over is the angular velocity omega. So then therefore, when you integrate and plug in your limits here on the right-hand side of the expression, you end up with the following. And then let's just go ahead and move the initial value to the other side of the expression. And then lo and behold, right off the bat, there's our first kinematics equation. Okay, I'm doing this fairly quickly because you've seen this process before, of course. We did this back in one-dimensional translational motion for constant acceleration. It's basically the exact same mathematical process here, just with slightly different symbols. So this right here is obviously the rotational equivalent of v equals v naught plus at. And now we integrate one more time to go from angular velocity to angular position. Here's then how we do that process. So we have angular velocity is the derivative of angular position with respect to time. So we're going to integrate one more time. So let's go ahead and move the time here to the left like so. And then on the left-hand side, we're integrating over time from 0 to t. On the right-hand side, we're integrating over angular position from an initial value called theta naught to a final value theta. Now, when we do integrate the left-hand side of the expression, keep in mind that the angular velocity omega is a function of time. It's this quantity here. So let's go ahead and plug that in to the left-hand side of the expression. So then therefore the left-hand integral becomes the following, like so. But then on the right-hand side of the expression, when we integrate over the angle here and then plug in the limits, you just end up with the change in angular position, like so. Okay, and then let's go ahead and integrate here on the left. When you integrate this quantity and plug in the limits, you end up with the following. There we go, like so. And then the last step is to move the initial angular position to the other side of the expression, and then therefore we end up with this. Like so. Once again, I did this fairly quickly because you've seen this process before. This is obviously the rotational equivalent of x equals x naught plus v naught t plus 1/2 at squared. If you recall back in chapter 2, we then algebraically combined the equations together to get the third kinematics equation. We could do the exact same thing here. In order to do so, what we would do is we would take this omega expression here and solve it for time t, and then ultimately we would take that time and plug it into here and here. If you do that process, here is then therefore the third kinematics equation. Like so. Okay, it's not necessary for me to show you the algebra to do this. It's the exact same series of steps that I did back in chapter 2. But this is pretty obviously the rotational equivalent of v squared equals v naught squared plus 2a times x minus x naught, like so, but now in terms of rotational quantities. Okay, so let's go ahead now and use these kinematics expressions to describe a couple of simple situations involving rotation about a fixed axis. We'll take a look at two problems. Let me go ahead and erase here first. Okay, and then let's go ahead and take a look at the first of these two problems. This one involves an automobile engine. Go ahead and write it down as I read it here. The rotation of an automobile engine is increased from 1200 RPM to 3000 RPM in 12 seconds. Part A, find the angular acceleration. Part B, find out how many revolutions or rotations are made. Okay, now I'm going to go ahead and write down our kinematics expressions here before we begin. Third kinematics equation. Like so. Okay, and now the question is what is exactly given here in this problem? Okay, well, first of all, the time is given, of course. The time is just given to us as 12 seconds. But then it says that the rotation is increased from 1200 to 3000 RPM. RPM stands for revolutions per minute. So what quantity is revolutions per minute? Is it angular velocity? No, it's frequency. So what we're given here is the initial frequency of the rotation and then the final frequency. So I'm going to refer to the initial frequency as F naught. This is given to us as 1200 revolutions per minute. Okay, I'm going to go ahead and convert this into hertz. Remember that a hertz is revolutions per second. So let's go ahead and multiply by 1 minute per 60 seconds. This will then give us this value in terms of hertz. So 1200 divided by 60, I can't do this stuff in my head anymore. And this comes out to be 20 hertz. However, from this quantity, let's now go ahead and get the angular velocity. In order to do so, we would have to go back to chapter 5 for just a moment when we looked at the kinematics of uniform circular motion. At the time, I wrote down the following equation, but you haven't seen it since. The initial angular velocity in this problem is 2 pi multiplied by the initial frequency, F naught. So take this quantity here and multiply it by 2 pi. Yeah, I'll just write this as a decimal. That's perfectly fine. This is about 125.66, and this would be radians per second. So when you're given RPM, you have to realize that what you're given is frequency in this problem. Okay, then we'll do the same thing for the final value of the frequency. The final value is given to us as 3000 RPM. So that's 3000 revolutions per minute, multiplied by 1 minute per 60 seconds. Convert this into hertz. So 3000 and then divided by 60. Once again, I can't do this stuff in my head anymore. This is 50 hertz. And then from there, we'll go ahead and now find the final angular velocity, omega, 2 pi times net frequency. Like so, so times 2 times pi, and this works out to be 314, it's actually a multiple of pi, 314.16 about. This would be radians per second when talking about angular velocity. There we go. Like so, okay? Okay, now let's go ahead and actually do part A of the problem. In order to do part A of the problem, we'll use this second kinematics expression here because we do know what the two values of the angular velocities are, and the time is given. So just solve for alpha. So move omega naught to the other side, divide by t. You do the math here, like so. And you end up with the following. Okay, so I'm going to go ahead and take this value here, 314.16. 314.16, there we go. And then subtract from that 125.66, and then take all of that and divide it by the time of 12 seconds. This comes out to be about 15.7 or so radians per second squared. Like that. Okay, easy enough for part A of the problem, but now in part B, it's asking for how many revolutions are made. What exactly is being asked for here? What's being asked for is the angular position theta. Because once I know what the total amount of radians is that the object is rotated through, then we can go ahead and from there figure out how many revolutions have been made. So when a problem is stated in that manner, what you have to realize is what they're asking for is the angular position. That's typically how the angular position is described in a rotational situation. Okay, so for part B of the problem, then all I'm going to do is just plug everything in for theta, like so. So we have, first of all, the initial angular position, which we just assume is 0, as we did with translational motion back in chapter 2. And now I'm going to go ahead and take omega naught, so 125.66 multiplied by 12 seconds, plus 1/2 times the acceleration of 15.7 times then the time squared. And ultimately I end up with 3015.3 or so radians. And then from there, I would obtain the number of rotations or revolutions by taking that value of 315.3 radians and then dividing it by 2 pi radians per revolution, like so. So show all the units here when doing these basic calculations to make sure that you understand how this works. Radians cancels out, and we end up with a certain number of revolutions. So divide by 2 times pi, make sure you use parentheses in the denominator when doing this, and it's like 480 revolutions, like so. Okay, pretty obviously this first kinematics problem is simple and straightforward, and it's involving an object that's spinning up. Okay, now for the second example, let's see what happens when an object spins down. Okay, I'm going to do some erasing here. And then we'll take a look at the second example. So let me go ahead and move my file. Okay, so in this case we have what is called a flywheel. A flywheel is usually a large disc of some sort. When it rotates, it then stores for you rotational kinetic energy. So because it involves a rotation, this allows you to store energy as kinetic energy in a small space. So that's what's referred to as a flywheel. Okay, so a flywheel completes 40 revolutions while coming to rest from an initial angular speed of 1.5 radians per second. Find the angular acceleration and how much time was necessary for this to happen. Okay, so once again, the question is what's given? Well, let's just start off with the initial angular position as 0, and the final angular position is what happens after 40 revolutions. So then therefore what I have to do is I have to convert that into radians. So think of it like this. We have 40 revolutions, and then we'll multiply by 2 pi radians per revolution. Once again, showing how all of the units here work out. So this ends up being 80 pi. So let me go ahead and figure out what that number is as a decimal on my calculator. So 80 pi is like 251.3 or so. And this would be radians when talking about the angular position. Okay, and then the initial angular speed is given to us as 1.5 radians per second. And because the object comes to rest, the final value, omega, is equal to 0. And now in part A of the problem, it asks to find the angular acceleration. So in order to find the angular acceleration for this example, we'll actually use the third kinematics equation here to do so. So let's go ahead and plug in our zeros. So the object comes to rest and it starts at the origin. So I plug in my zeros like so. And then run through the algebra here to solve for the angular acceleration alpha. So when you do and move things around and so forth, you end up with this expression here. So now let me go ahead and figure out what this is. So I actually still have this number here in my calculator. So let me go ahead and do the denominator here first. So times 2, take the reciprocal, and then times 1.5 squared, and it's negative. It's about negative 0.0045 about radians per second squared. Okay, now what do you suppose the negative sign means? You're probably sitting there and saying to yourself, oh, it means that the flywheel is slowing down. No, it means that there is a direction associated with a vector. Remember what happened back in chapter 2 when talking about the kinematics quantities. Periodically, we examined situations where the acceleration vector was a negative number. And you would, for example, say to yourself, oh, that means the object is slowing down. No, as you saw, that meant that the acceleration vector pointed in a specific direction, in the negative direction, for example. So then therefore, if you pick up a negative number here for angular acceleration, you might say to yourself, oh, that means that the flywheel is slowing down. No, it means there's a direction. Somehow there are vector quantities associated with these rotational quantities. It's not obvious, however, what the directions of the vectors are. I'll get to that in the next lecture. Before I do, however, let's just go ahead and complete this problem. So in part B of the problem, it now asks us to calculate the time necessary for this rotation to occur such that the object spins down. Okay, in order to do so, we'll just go ahead and use this expression here where the final angular velocity is 0. Like so, and now just solve for the time t. So move this term to the other side and divide by alpha. And we end up with this expression here, but notice that the negative signs will now cancel out to give us a positive time. All right, so I actually still have this angular acceleration here in my calculator, so let me go ahead and put it up into the numerator, and then multiply by 1.5. All of the negative signs cancel out, and this ends up being just over 5 minutes, 335 seconds. Like so. Obviously, these are easy examples to complete, and I did these fairly quickly because you've seen problems like this before, but now just in terms of rotational quantities. But particularly in the second of these two examples, I am implying that there are directions associated with these rotational quantities. What those directions are, I'll get to in the next video.